Hello folks, this video is about the uh, derivatives of natural exponential functions, natural log functions. So it's basically like ln functions, and I'll briefly go over some examples and what the well-known facts are. The first, like the basic first function that we know is f of x equals ln x, and you can put g of x equals ln absolute value of x in the same category. They have the same derivative. The difference is that in the first one you can only plug in positive values, and here you can plug in any value for x other than 0. So the derivatives of both functions, this is same for f prime of x or g prime of x, they're both the same 1 over x. So that's the first fact that we have. The derivative of ln function is 1 over x. Just a simple example, if you take f of x equals to be 5 times ln x, then its derivative f prime of x will be 5 times 1 over x, which is namely 5 over x. So this is how we find those, find the derivative of a ln function, which is a multiple, which is a constant multiple of the main ln function. So let's take a look at the different example. Consider this one: y equals x to the third ln x plus 4x. So how do we find the derivative of this one? If you look at here in this function, yeah, we know the derivative of 4x is 4. The derivative of 4x is 4, but for the first part we have a product. So we need to use the product rule in here. Product rule. Remember the product rule? If you take the derivative of a first second, like a product of the form first second, it's going to be first prime times second plus first times second prime. So this is my first function, this is my second function. So let's take the derivative y prime. That's going to be derivative of first one, which is 3x squared times ln x plus x to the third times derivative of ln x is 1 over x, plus we have 4x, we have just 4, because derivative of 4x is simply 4. So we can we have a simplification here, like x to the third and x, they'll cancel and you got an x squared. So if you simplify this derivative, it's going to be 3x squared times ln x plus an x squared plus 4. So it's pretty easy, not that bad when you have a combination given as a product. Use the product rule. Now the next one, the next example that we may have is when you have now a quotient, like let's say y equals ln x divided by x squared. Now we want to find the derivative of this function. Of course, you see we're going to be using, obviously it's a quotient, so it's going to be the quotient rule. So quotient rule says if you have a quotient of the form top divided by bottom, if you take the derivative of this, this is going to be top prime times bottom minus top times bottom prime and divided by bottom squared. So we can use this quotient rule here. So y prime will be derivative of top 1 over x times x squared minus ln x times derivative of x squared, which is 2x, and whole expression divided by x squared squared. Please folks, sometimes I see some students combining this x and 2x. You can't combine them. Ln x, actually ln is the name, so ln is just simply applied to x. This is ln x. So that's why you can't combine them. That x belongs to ln, whereas that 2x is just a polynomial. so you can't combine them, combine x into x. So here you can simplify x and x squared, you will get an x. So we have x minus 2x times ln x divided by x to the 4. You can simplify further. Why? I can factor out an x. I got 1 minus 2 times ln x. So we got x times 1 minus 2x and divided by x to the 4. And x and x to the 4 cancel, and I got x to the 3rd. And then, so the answer will be final answer 1 minus 2 times ln x divided by x to the 3rd. That's what we have. Now, we have a similar rule that we had in the exponential functions. Remember, that's kind of a recall. If you want to find the derivative of something like e to the f of x, that was e to the f of x multiplied by f prime of x. That's what we had. Now, in the ln case, if you want to find the derivative of something like ln of f of x, so it's kind of that f of x is the inner function, the outer function is ln. This is the outer function, and then this is the outer function, and this f of x is the inner function. So you take the derivative of the outer function, ln, which is 1 over x, and you keep the inner function instead of x. So it's going to be 1 over f of x, and multiply it by the derivative of the inner function, which is f prime of x. So you get like f prime of x divided by f of x for the derivative. And this is the exact, what we have. Again, the rule here that we apply is the chain rule. So, some examples. Take a look at this example. So, how do we find the derivative of ln of, for example, 3x? So, it's going to be 1 over 3x times the derivative of 3x, which is 3. And you see you can simplify 3's, and we just get 1 over x. So every time, because this ln 3x can be broken down as ln 3 plus ln x. So ln 3's derivative will be 0. So that's why you get 1 over x, the same as the derivative of ln x. But that's how you use this rule. Here we go, another one. Consider this one. So let's say you want to take the derivative of ln x to the 4 plus x. So you want to take the derivative of this function. So it's going to be 1 over whatever you have function inside ln, inner function x to the 4 plus x, times it by the derivative of the inner function, which is 4x to the 3rd plus 1. So it's like 4x to the 3rd plus 1 divided by x to the 4 plus x. So now if you look at this, you can clearly see the top is inner prime and the bottom is simply the inner function. You can just see that it's like f prime, so it's just the same formula. See, you have the same formula right in here. F of x is the inner function, so ln of f of x is derivative is a fraction in which the top is the inner prime and the bottom is the inner function. So, okay, we have some more examples about this. Like consider this one. Here's another example. So you want to take the derivative of f of x equals ln of x. See now, in this case, the outer function is ln and the inner function is also ln. So it's kind of like you have the same function for that. So when you take f prime, derivative of ln is 1 over x, but you keep ln in there, so it's going to be 1 over ln x. You keep ln inside the derivative of ln, times it by the derivative of ln, which is 1 over x. And if you combine this, it's going to be 1 over x times ln x. So, and folks, here's another example. So it's like y equals ln of x to the 4 plus 4. Right, wrong, x to the third. Say x to the third plus 4 divided by x. For these type of functions, you have a rule to make our problem really simple. We have these facts, the product rule and the quotient rule for the ln. So if you have ln m times n, you can write this down as ln m plus ln n. Product inside ln becomes the sum of the ln's. And if you have ln m over n, that's going to be ln m minus ln n. So these are the rules that we have. So it's kind of better to apply that in this problem, because in that case you will take the derivative of the whole thing, 1 over the whole thing for ln, and then use the quotient rule. Maybe you can simplify by dividing by x, but this way will make it the easiest. So you can write y as ln x to the third plus 4, and then minus ln x. So you take the derivative of first one, y prime, which is 1 over x to the third plus 4 multiplied by 3x squared, which is the derivative of the inner function, minus 1 over x. So that's going to be 3x squared divided by x to the third plus 4 minus 1 over x. This is the derivative of this function. Or, for example, just write down a more short example. So if you for example take y equals ln, this is another example. Y equals ln x to the 4 plus 1 multiplied by 3x squared plus x minus 1. See, this is now a product inside ln. So you can definitely write this as ln x to the 4 plus 1 plus ln 3x squared plus x minus 1. So I'm using that fact, product rule for the logs. So in this case, you take the derivative of the inner function, which is 4x to the third, divided by the actual function, which is x to the 4 plus 1, plus derivative of the function is 6x plus 1, divided by the actual function, inner function, 3x squared plus x minus 1. So don't forget, it was like the derivative of ln f of x was f prime of x divided by f of x. You can use that rule, like just the final conclusion of that rule. Okay, I hope we're doing great so far. Now, this was one of them. Now, one last example. This is like this is an application problem. Let's say the cost function for an item is given by c of x equals 800 times x plus 520 times ln x. Here x is just the items produced. So the first question is this: what is c of 100 and what is c prime of 100? And we're going to write the meanings for them. So the first one is really simple. C of 100, you'll simply plug in 100 in the function. So it's like 800 times 100 plus 520 times ln 100, which gives us $82,394.69. This is the cost of producing 100 items. Okay, could be like a machine, something a little bit expensive, but yeah. If you want to find the rate of change now, you need to find c prime of x. You see derivative of 800x is just 800 plus 520 times ln x is just 1 over x. So you got 800 plus 520 over x. This is the derivative of the cost function. We call this the derivative of cost as the marginal cost. Let me just write that definition right here, which might be helpful. Marginal cost. So now we plug in 100 to this. So it's going to be 800 plus 520 divided by 100, which is 805.20 per year. So what we get, because this is the rate of change, folks, don't forget. So that means cost is increasing at a rate of 805.20 per year when 100 items are produced. So that's kind of the rate of change when that particular number of items are produced. I hope you liked the video. So this basically covers the derivatives of natural exponential functions. See you next time. Thanks for watching. Bye.